Our journey begins in the vast expanse of space, amidst cold, dark clouds of gas and dust. These cosmic clouds, known as nebulae, are the birthplaces of stars. Don't let their darkness fool you. These clouds teem with the raw materials of creation. Hydrogen, the simplest and most abundant element, dominates these clouds. Helium, a close second, also plays a crucial role. Interspersed within these clouds are remnants of past generations of stars, their ashes containing heavier elements. These elements will eventually become the building blocks of planets and even life itself. These cosmic clouds are not static entities. They are constantly in motion, stirred by gravitational forces and the shockwaves of distant supernovae. Over eons, these forces can cause regions within a cloud to become denser. As the density increases, so does the gravitational pull. This sets the stage for the birth of a star. Within the depths of a collapsing cloud, gravity begins to exert its dominance. The denser regions pull in more and more gas and dust, causing the core to collapse in on itself. This core, known as a prestellar core, continues to shrink under its own weight. As it shrinks, it spins faster and faster, much like a spinning figure skater pulling in their arms. As the core collapses, the temperature and pressure at its center skyrocket. The once cold and dark cloud now glows with an eerie infrared light. This glowing core, still shrouded in a veil of gas and dust, is known as a protostar. The protostar is not yet a true star, but it is well on its way. Surrounding the nascent protostar is a swirling disk of gas and dust known as a solar nebula. This nebula, sculpted by gravity and angular momentum, provides the raw materials for the formation of planets and other celestial bodies. Within the disk, dust particles collide and stick together, gradually growing larger and larger. Over millions of years, these dust grains coalesce into planetesimals, the building blocks of planets. Closer to the protostar, where temperatures are higher, rocky planets like Earth form. Farther out, in the cooler reaches of the nebula, gas giants like Jupiter and Saturn accrete massive atmospheres of hydrogen and helium. Section 4. Ignition. The protostar ignites. Deep within the heart of the protostar, the temperature and pressure continue to rise relentlessly. Eventually, the core reaches a critical temperature of about 10 million degrees Celsius. At this temperature, a remarkable transformation occurs. Nuclear fusion begins. Hydrogen atoms, forced together under immense pressure, fuse to form helium atoms, releasing a tremendous amount of energy in the process. This energy, radiating outward from the core, creates an outward pressure that counteracts the inward pull of gravity. The protostar, finally achieving a state of hydrostatic equilibrium, ceases to collapse. It has ignited, transforming from a collapsing cloud of gas and dust into a true star. Section 5. Stellar maturity. A star is born. The newly ignited star, now shining brightly with the light of nuclear fusion, enters a long and stable period of its life, known as the main sequence. During this phase, the star will continue to fuse hydrogen into helium in its core, releasing a steady stream of energy that sustains its luminosity. The length of a star's main sequence lifetime depends on its mass. Massive stars with their intense gravitational pull burn through their hydrogen fuel much faster than their smaller counterparts. These stellar giants live fast and die young, exhausting their fuel in a few million years. Smaller stars, on the other hand, sip their fuel slowly and can live for billions or even trillions of years. Section 6. Stellar Afterlife. From red giant to white dwarf. As a star ages, it gradually exhausts the hydrogen fuel in its core. With nuclear fusion dwindling, the outward pressure that once balanced gravity begins to wane. The core contracts, heating up even further. This heat causes the star's outer layers to expand outward, transforming it into a red giant. During its red giant phase, the star will fuse helium into heavier elements, such as carbon and oxygen. Eventually, even these heavier fuels will be exhausted. For a star like our Sun, the final stage of its life is a white dwarf.